Welcome to the next lecture in Math 1342, Elementary Statistics at Dallas College with Professor Bailey using ALEKS. Here we're going to look at constructing a sampling distribution of a sample mean and using the central limit theorem to compute probabilities. In real situations, statistical studies involve sampling several individuals, then computing numerical summaries of the samples. Most often, the sample mean, or the average of all the data collected, x bar, is computed. If several samples are drawn from a population, they are likely to have different values for x bar. We wouldn't expect that each sample of 10 people or 10 items would have the same average. So it's very likely that they're going to have a different mean x bar. Because the value of the x bar varies each time a sample is drawn, x bar itself is a random variable. For each value of the random variable x bar, we can compute a probability. The probability distribution of x bar is called the sampling distribution of the sample mean x bar. So let's look at an example to help us understand this a little bit more clearly. Tetrahedral dice are shaped like a pyramid with 4 faces. A normal die is a cube with 6 faces, so this is very similar to problems we've done before with probability. On a tetrahedral dice, each face corresponds to a number between 1 and 4. Tossing a die is like sampling a value from the population, and we could have 4 possible samples or results, outcomes: 1, 2, 3, or 4. That is, when we roll the die, we will either get a 1, 2, 3, or 4. We can easily find the population mean and population standard deviation from this. The population mean is all the possible outcomes over the sample space, and that gives us, this is our average value. Remember, when we talked about this in probabilities, and we would get a mean of 2.5. The population standard deviation, calculated by taking each of the possible outcomes minus the average over the sample size, gives us this standard deviation of 1.118. Suppose now that we toss the die, the tetrahedral die, 3 times. The sequence of 3 numbers is observed, may be thought of as a sample of size 3. We might get samples such as 111, 112, 113. Again, if you think back to how we've done this with tree diagrams, you'll see all those possibilities. Here we see actually all the possibilities if we went ahead and drew the tree diagram out. You can see here in the first one, this is where we roll 3 die and we get a 1 on every one. Well, the average of this, or the mean, is 1, right? 1 plus 1 plus 1 over 3. In the second one, we get 1 plus 1 plus 2, which is 4 over 3, 3 throws, and that average is 1.33. So here's a good example where you can see the average of each of the experiments, of each of our samples, is slightly different. Okay, and this is the idea that the x bar, the mean of the sample, will be different. The table displays all possible samples of size 3 and the sample mean of each. The mean of all values of x bar is mu sub x bar equals 2.5, and the standard deviation values of x bar is 0.6455, and you can see that here. Next, we're going to compare these values to the population mean and the population standard deviation. What's interesting about this, and this is why it's very useful in statistics, is that the mean of the sampling distribution, mu sub x equals 2.5, which is the same as the mean of the population, mu equals 2.5, this relationship always holds. And the mean of the sampling distribution equals the mean of the population. So this is something we can rely upon, and it helps us figure out those probabilities. When we look at the standard deviation between the population and the sampling distribution, it's not the same. And it's not obvious how these quantities are related, but they are related by a very simple formula. Specifically, the standard deviation of the sample distribution is equal to the population sample mean divided by the square root of the sample size. And remember, in this case, we were tossing the die 3 times, so we get the population standard deviation over the square root of 3. Sometimes this is called the standard error, so that why is there the difference between a sample and the standard deviation difference between the sample and the population. All right, so here's a problem. I want you to try, hit pause, and then try this problem. When you've got an answer, go ahead and hit play and see if you've done okay. Among students at a certain college, the mean number of hours of television watched per week is 10.5, and the standard deviation is 3.6. A simple random sample of 16 students is chosen for a study of viewing habits. Let X bar be the mean number of hours of TV watched by the sample students. Find the mean of the sample distribution and the standard deviation of the standard deviation. Again, we have these two formulas. The mean of the sample distribution is the same as the mean for the population, so this is really simple. The standard deviation for this sample distribution is equal to the population standard deviation over the square root of our sample size. In this case, our sample size is 16, so we get a standard deviation of the sample distribution equals 0.9. Hopefully you did try that and could figure that out. It's a direct and simple kind of calculation, but actually doing things is much better than watching me talk about doing things or reading the example in the book. Trying it ahead of time allows you to see where your struggles are, and everything you do actively, you recall better. Let's try another one. Hit pause and try this. Remember your formulas. And here's the answers. I'm not going to plug these in or talk about this. It's just another problem for you to practice. Hopefully you did. Okay, so let's go back to our example for tossing a tetrahedral die with a sample size of 3. The sampling distribution for X bar can be determined from the table of all possible values of X bar. The probability that the sample mean is 1 out of 64. Now, how do we get that? Well, notice of all of these averages, of all of these, means for, there are 64 different possible results from throwing the tetrahedral die 3 times, and this is, based upon our tree diagram, right? The first throw we have 4 different possibilities, 1, 2, 3, 4. The second, we have an additional 4 possibilities for each of the first 4, etc. So we basically have 4 cubed possibilities, which is 64. We can count them all here, and we can see that 1 only happens 1 time out of those 64, so our probability is 1 out of 64. If we look at an X bar value of 1.33, we can see that this happens 3 times in our sample space of 64 possibilities. And so this is 3 out of 64 probability, or 0.047. Okay, so here we see our probability distribution table. Here's our mean for the sample distribution, for the sample mean. Here we see the probability of each of those possible outcomes. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes, and these are the related probabilities for each of them based upon how many times each of these x bar or sample means appears in our sample space divided by 64 possibilities. In the tetrahedral die example, the population is 1, 2, 3, 4. This is the entire sample space that's possible when we roll the die. When we roll the die, each number has the same chance of appearing because it's a fair die. So each number, 1 for example, rolling a 1, we have a 1 in 4 possibility, or 0.25. And that's the probability table you see to the right. Each of the rolls, each of the outcomes is equally likely with a fair die. The probability histogram for the sampling distribution of x bar, this is that table of 64 values with the sample size 3, is shown here. And we can see that this is a normal curve, whereas the probability histogram is certainly not. It's a constant histogram. What's interesting about this, and this is why this is such a powerful tool looking at these samples, is that it is true that for any population, if the sample size is large enough, the sample mean will be approximately normally distributed. For a symmetric population like the tetrahedral die population, the sample mean is approximately normal distributed even for a relatively small sample size of just doing 3 rolls of that die. But again, this works for any population graph, assuming the sample size is large enough. If a population is skewed, as you can see to the right here, a larger sample size is necessary for the sampling distribution to be approximately normal. And when we look below, we can see the probability histograms for the sampling distribution of x bar for samples of size 3. And you can see at size 3, the sample size, that we're still skewed to the right. When we get to sample size 10, we're much more normally looking, but still a small skew to the right. But this would be relatively normal. And then when we get to sample size 30, it's almost perfect. There's a little bit of overage on the left and a little bit of undercounting on the right, but in general, that's an approximate normal curve. The size of the sample needed to obtain approximate normality depends mostly on the skewness of the population. Remember, that's what we saw up here, okay? So the more it's skewed, the larger the sample size we're going to need. In practice, a sample size of n is greater than 30, or a sample larger than 30, 30 or larger really, is generally large enough. This remarkable fact that the sampling distribution of x bar is approximately normal for a large sample from any distribution is one of the most used theorems in statistics, and this is called the central limit theorem. As soon as we can get data into a normal curve, remember then we can use the z-scores and the normal curve rules about how much data is within 1, 2, and 3 standard deviations. So this is a really powerful tool for statistics, specifically to take a sample, the data we collect from a sample, and make opinions or thoughts or inferences about the population as a whole. So the fact that this works is really a powerful, probably one of the most powerful tools in statistics. The central limit theorem. Let x bar be the mean of a large sample, n greater than 30, from a population with mean mu and standard deviation sigma. Then x bar has an approximate normal distribution with the same mean, mu sub x bar equals the population mean, and a standard deviation, which equals the standard deviation of the population over the square root of n, which is the size of the sample. This central limit theory applies for all populations. However, for if the original population is symmetric, you can use a much smaller sample size. If the population itself is normal, the sample mean will be normal for relatively any sample size. So let's try another problem here. Let's see this central limit theorem working and see if you can calculate this. Recent data from the U.S. Census indicates that the mean average of college students is 25 years, with the standard deviation of 9.5 years. A simple random sample of 125 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? So I want you to hit pause and try this, but first I want you to remember that with this kind of normal curve diagram, if we calculate the z-score, remember if we have that z-score, we can look in the table 2, which you are allowed to use on the next test. You can look at table 2 and calculate the probability, remember the probability or proportion is the area under the curve to the left of whatever value. Okay, so try this value, or try this calculation. Hit pause and try this. So the first thing we need to do is to figure out, can we use the normal curve? Since the sample size is 125, which is greater than 30, we can use the normal curve. We're not going to do any more calculations beyond that. Then we need to calculate our mean and standard deviation for our sample. So we know that the mean is equal to the population mean, and we know how to calculate our standard deviation for our sample by taking the population standard deviation divided by the square root of 125, and we get 0.85 for the standard deviation and 25 for the mean. Remember, in order to calculate a z-score, all we have to do is plug in these values for x, the mean, and the sigma. Well, our x value is here. It was 26 years. These are what the axis is. The x-axis values are here. So we're looking for 26 minus our mean, all divided by our standard deviation. Okay, when we find that, we find a z-score of 1.18. Okay, we would expect that because remember, z-scores represent the number of standard deviations away from the average or the mean. If it's to the right, it would be positive. If it's to the left, it would be negative. Remember, the values inside the table represent the probability or the proportion or the percentage, all of those concepts, of the area to the left of the table. So when we look at that value in table A2, remember that all z-scores have 2 decimal places. On the left column, you're going to go down to 1.1, and then you're going to go over to the right of all the values until you hit the column titled 0.08, because 1.1 plus 0.08 gives us 1.118. When you look at that value, you will find in table A2 0.8810. Okay. Now you may be quick to think, okay, well that's the probability that someone is greater than 26 years, but that is wrong. Remember that table A2 gives you the probability to the left. So this probability is that the probability that the sample mean age of the students is less than 26 years. So there's an 88% chance that the mean is less than 26 years. And so remember, if we're trying to find a greater than value or an area to the right, we have to take 1 minus the value in the table, right? Because the whole area under the curve is equal to 1. This is a proportion of the area to the left, so 1 minus that will give us the shaded area that you see here to the right. So our actual probability is 0.1197, or approximately 12%. We have a 12% or 0.12 probability that the mean age of the students is going to be greater than 26 years. The mean age of college students, mu, is 25 years with a standard deviation of 9.5 years. A random sample of 125 students is drawn. So this is the same pool that we looked at before. Again, another sample. In this case, we want to find the 30th percentile of the sample mean. Can you remember how to do that? Again, using table 2 of the z-scores. Okay. Hit pause and see if you can do this. Well, we already calculated both of these before, so I'm just plugging them in here again. Again, the sample distribution mean is the same as the population, and the standard deviation is population standard deviation over the square root of our sample size. Remember that the 30th percentile, think Texas STAR test or something, is where you fall in line. So if you got, let's say you're in the 30th percentile of the SAT, that means you scored better than 30% of the other people taking the test, and 70% scored higher than you. So this is the proportion of people right at that value. Remember that the proportion or percentile or probability is the area to the left, okay, in the table A2. So what we're looking for is the area 0.30 in the table, okay? And then we're trying to find that x value that correlates to. So the first thing we have to do is find the z-score. Then we can re-engineer the z-score formula to find the x value, which we've done before in prior chapters and sections. Okay, this is the reworked formula. We looked at the z-score before. So if we're trying to find an x value given a z-score, this is just rewriting the formula to solve for x. The score 0.30, now you're looking inside the table at all the data, and then you're trying to figure out the z-score from the first column and the row along the top. Okay, so the z-score is for 0.30 is between 0.52 and 0.53, negative 0.52 and negative 0.53, which we would expect because it's below the mean. So we're going to use the value exactly in between. So we're going to use something that's not on there. Since it's roughly midway between these two values, we don't have an entry in the table that's exactly 0.3000. So we're going to use negative 0.525 for our z value. All we do is plug in the rest of these values, the mean and the standard deviation. As you can see, the mean plus our z-score times the standard deviation, making sure that you recognize it's negative, and we get our x value. Here you can see it with the TI-84 calculator. So an age of 24 and a half, basically 24.5, is the 30th percentile. The 30th percentile of the sample mean x bar is approximately 24.55 years because the x represents the number of years. Let's try another one. This is a new example. Again, read through it, hit pause, and see if you can complete this. Hereford cattle are the most popular breeds of cattle. Based on data from the Hereford Cattle Society, the mean weight of 1-year-old Hereford bull is 1,135 pounds, with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 cattle to be less than 1,100 pounds? So remember from prior that a score is unusual if it has a probability of less than 0.05, or basically that this probability or area or proportion or percentage is less than 0.05 or 5%. Okay, so all we're going to do is find the area to the left here and see if this area is less than 0.05. See if you can do that by hitting pause and trying this. So we're given the average weight of the population, the standard deviation of the population. We know that we have a sample size of 100 and we have the x value. So let's first calculate the mean of the sample distribution and the standard deviation. Also, we know we can use the normal curve because the sample size is greater than 30. So our sample mean is the same as the population, and we've calculated the standard deviation here to be 9.7. We need to find the z-score so we can find the area under the curve, and in this case it is exactly the z-score because remember the z-score represents the area to the left, which is what's showing in our diagram. It's often helpful to draw these, labeling the mean and then figuring out what your x value is, or if it's a percentage below 50% or above, etc. Anyway, let's continue on. So our z-score, we plug in the x value we're looking at, 1100 minus our mean, 1350, all over our standard deviation, and we get negative 3.61. We go to the z-score table, A2. We look along the first column and we go to negative 3.6, and then we go across the row to the top until we find 0.01, and we look at the value there, which is 0.002. 0.002 is much less than 0.05, which is 5%, so it would be very unusual for the sample mean to be this low. Here's a couple more problems. I'm not going to walk through these, but I do have the answers here. So if you want to hit pause and try these are very straightforward problems like we've just been doing. These are the topics we just covered: how to construct the sampling distribution of a sample mean, how to find the mean and standard deviation, central limit theorem, and how to use the central limit theorem to compute probabilities. A little joke here. Can you write the next line? I had an argument with a 90-degree angle. This is like a math dad joke. Turns out it was right. But bad joke, I know. In 6.3, and this time we're covering two sections. You might want to make a pause here and come back to this later. But in 6.3, we're going to construct the sampling distribution for a sample proportion and then compute probabilities as well. So this is like the sample mean, but now we're doing proportions. It's very similar. In a population, the proportion who have a certain characteristic is called the population proportion. The population proportion is denoted by P. So we look at a population, we might say what proportion of this population is female, and that would be what we're given there. And then we take a simple random sample of n individuals from the population. Let x be the number in the sample who have the characteristic. The sample proportion then, which is called p hat, is the number that have that characteristic. In our example, the number of females over the total number that we polled. Okay, this is called p hat, the sample proportion. Simply the number of people that have that characteristic in our sample over the number of people that we actually sampled. Pretty straightforward. Computer retailer wants to estimate the proportion in her city who own laptops. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops, so our proportion is 35 over 100, or 0.35. Remember, the proportion in the entire city that has that is a different variable. P, not p hat. This is just a sample. If several samples are drawn from a population, they are likely to have different values for the sample proportion, because the value of the sample proportion, p hat, varies each time a sample is drawn. Therefore, just like the sample mean, p hat is a random variable and it has a probability distribution. The table looks very simple again, but now instead of averages or means, we're looking at proportions. So let's look at another example. Consider tossing a fair coin 5 times. This produces a sample of size n equals 5, where each item in the sample is either a head or a tail. The proportion that the coin lands on head is the sample proportion p hat. The probability that it lands heads each time is 0.5, so the population proportion of heads is 0.5. Next, we look at all 32 possible samples that can be constructed. So again, we've seen this before with our tree diagrams. Here we're flipping a coin 5 times. So the first thing we could get is tails, 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 tails. Well, our proportion is the number of heads that we get, right? So we have 0 heads over 5 flips. We get a proportion of 0.00. If we do it again, and the last one is a head, we have 1 out of 5, so our proportion is 0.2. If we have 2 out of 5, then we have 0.4. And you can see how we have these different probabilities, or proportions, I should say, for our sample distribution. Okay? The mean of all of these values of p hat is 0.5. And the standard deviation of all the values of p hat is 0.2236. Let's look at how these compare. So our p hat is exactly the same as our population proportion. When we do a large number of samples, we would expect that the mean of all the values of p hat would be equal to the proportion of the population, or lowercase p. So just like the sample mean, the sample proportion is equal to the mean of the sampling proportion is equal to the population proportion, okay? So here we're looking at a proportion in the population. Our average or mean of all of our samples proportion is equal to that population proportion. And here we have a slightly different calculation for the standard deviation of the sample proportions. And specifically, as the standard deviation of the sampling distribution of p hat is the proportion from the population times 1 minus that proportion from the population all over the size of our sample and the square root of that quantity. Okay, so these are the formulas we're going to use. It's a little bit different than the sample mean. So these are important for you to know and have in your notes. So here are 2 different examples. Ignore the try another until you've done the first one, but I would suggest that you try these. Hit pause and try these problems and then come back. Alright, the soft drinks at a certain fast food restaurants have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is p equals 0.25. Now remember, this is the population proportion. A total of n equals 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let p hat be the proportion that win a prize. Find the mean and standard deviation of p hat. All right, so we know that the mean of p hat is equal to p. And we can calculate the standard deviation of p hat, which is p, the square root of the quantity of p times 1 minus p all over n, p being the population proportion and n being our sample size. Okay? So that's all I'm asking you to do here, is first to be able to calculate those values. So do the same thing with those formulas for the values below, and you hopefully will get this. Again, try it, or if you haven't already. The probability histogram for the sampling distribution of p hat for the proportion of heads in 5 tosses of a coin is presented. We can see that the distribution is reasonably well approximated by a normal curve. The If we do the experiment again, but with 50 tosses of a fair coin, we can see as we increase the number of tosses that the sampling distribution is more closely approximated by that normal curve. When p equals 0.5, the sampling distribution of p hat is somewhat close to normal even for a sample size like n equals 5. But when p is close to 0 or close to 1, a larger sample size is needed before the distribution of p hat is close to normal. Do you know what it means when I say that p is close to 0? Remember, p is the population proportion. So for example, we were talking about the proportion of a population that's female. So if that proportion is close to 0, then that means that our entire population is largely made up of males. If that proportion is close to 1, again, p representing the number of females or the characteristic of being a female, this means that our group or our population consists largely of females. So when your proportion is skewed to being hardly any in the group or almost all in the group, then you need a much larger sampling distribution for it to be normally distributed. So we use a common rule of thumb that the distribution may be approximated with a normal curve whenever the sample size times the proportion is at least 10 and the sample size times 1 minus the population proportion is also at least 10. Both of these occurrences have to be true for us to assume that the distribution can be approximated with a normal curve. So this is the first test we're going to do for most of our probability calculations for proportion distributions. We can now state the central limit theorem for proportions. The central limit theorem for proportion says that p hat be the sample proportion for a sample of size n from a population with population proportion lowercase p. If n times p is greater than or equal to 10 and n times the quantity of 1 minus p is greater than or equal to 10, then the distribution of p hat is approximately normal with the mean, mu of p hat, equaling to the population proportion, or lowercase p, and a standard deviation, sigma sub p hat, equaling the square root of the quantities of p times 1 minus p over n. Again, p representing, lowercase p representing the population proportion, and n representing our sample size. So again, you can see, first thing we have to do here is do this test. If we pass the test, if these calculations are both equal to or greater than 10, then we can go on and assume normality, which allows us to make inferences about the samples and find specific probabilities or proportions. So here I'm just asking you if it's possible to calculate or to use the normal distribution. So we're just going to do those two calculations. Hit pause and see if you can do it. Remember, NP has to be greater than or equal to 10, and then n times 1 minus p must be also greater than or equal to 10. Hit pause and try these. So in the first one, you can see that the second calculation is only equal to 6, which is less than 10, so we cannot use the normal distribution. In the second one, or the top right, we can see that both of these values, one is 44, one is 11, so they're both greater than or equal to 10. We can go ahead and use the normal distribution. Here notice that one of the values is actually both of the values are exactly equal to 10, but that's okay, and we can use it. And the last one, we have values that are much greater than 10, so we can use it again. Okay. So let's look at an example. and see if you can solve this. It's best if you can go ahead and try to solve this on your own and hit pause. Okay? According to a Harris poll, chocolate is the favorite ice cream flavor of 27% of Americans. What is that 27%? That 27% is our proportion of Americans that like chocolate, so that's our population proportion. If we take a sample of 100 Americans, that's our sample size n, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30? So we're going to try to find the probability that the sample proportion of those who prefer chocolate is greater than 0.3. Okay, so the first thing we have to do is make sure we can use the sample distribution of the proportion to be a normal curve. So we do those two calculations, n times p, making sure that it's greater than 10 or equal to, it is, and n times 1 minus p, and it's also greater than 10. So we can use the normal curve. At that point, we calculate both the mean of p hat, or the sample proportions, as well as the standard deviation of p hat, or this distribution of proportions. Okay, so we get 0.27 for the mean, 0.044396. We can now calculate a z-score for this specific example, okay, where our x value is 0.30 minus 0.27, that's our mean, all over our standard deviation, right? So if we look in the table, when we do that calculation, we get 0.6757. Remember that z-scores only go to 2 decimal places, so we go to 0.68. You'll go down the first column till you find positive 0.6, and then go over until you get to the columns. Go across the rows until you get to the columns for 0.08. So you're at the row for 0.6, and then go over to the column for 0.8, and you'll see that that value in the table is 0.7517. Okay. Now again, we have to be careful here because we're looking at the probability greater than 30, and remember that table A2 represents probabilities less than, or to the left, the area to the left of the curve. Okay, this is not correct. 75% do not prefer chocolate. It's not a higher percent, remember, because this 75 represents the probability of less than 30. So if we want the probability of greater than 30, we have to subtract that from 1. Okay, and so we get a probability of 24.9%. This is the probability that our sample proportion will be greater than the 30%. Okay, so in 30% of our samples, we have a probability of basically about 25%, that about 25% of our samples will have a proportion greater than 30%. It gets a little confusing because we're doing proportions. A probability is sort of like a proportion again, right? The proportion out of 1, or a percentage. So these can get a little bit confusing when we're using percentages or proportions, even as our x values instead of actual numbers. Okay. So let's try another problem. Approximately 60% of eligible voters voted in a recent U.S. presidential election. If a sample of 88 eligible voters were polled, would it be unusual if less than half of them had voted? Again, remember, When we're talking about unusual, we're looking for percentages or proportions less than 5% or 0.05. Okay, so hit pause and see if you can do this problem. Okay, the first thing we want to do is make sure we can use the sample distribution, the normal curve. Okay, so we check n. Our sample size is 88 times our population proportion, which is 0.6 or 0.60 because it's 60%. All right, we can see that that is 52.8, so it's greater than or equal to 10. And then we take again our sample size of 88 times 1 minus p, or 1 minus 0.6, and we get 35.2. So that's our first check. We check the assumptions and we can use the normal curve. We then compute our average or our mean for p hat, or the population proportion, and our standard deviation for p hat, or the population proportion. I'm not going to go through those calculations. We've done 3 or 4 of those already. Okay, once we have this, we can now calculate our z-score. We're looking for less than half. Less than half, half is 0.5, so that's our x value, minus 0.6, which is our proportion, or our mean, all over our standard deviation, which is what we calculated. And we get a negative 1.91. Okay, again, since we're doing less than half, then we're in a lucky shape because the table is for values less than. Okay, in this case, you can see here's our mean, here's our value we're looking at, less than half, and we're trying to find the probability of the area there. When we look in table A2 for negative 1.91, again, remember we round to 2 decimal places because that's what our table gives us. We get that the probability, or the data, we go to 1.91, we go to negative 1.9 on the left column, go over 2.01, the second column, and look at that data entry, we get 0.0281, which is roughly about 0.03 or 3%. Again, remember it's unusual if it's less than 0.05, so it would be unusual for the p hat to be less than 50. Okay, to find that our average half of them would be less than 50. Here's some more examples. I'm not going to walk through these, but if you want to pause and try these, you can do that. So that's the end of our lecture. We've covered both 6.2 and 6.3 in this lecture. It's a bit long, but it is actually 2 sections. So sorry for that. I think going forward, I'll only record 1 at a time.